ladies and gentlemen, good morning. Right, so last time we ended off the figure chain drives selection study theme. So over there we looked at some selection sheets, the catalogs that we will need to perform these chain drive selections. So today we're actually starting with a new study theme, and that's on the fundamentals of additive manufacturing. So we're going to look at what is manufacturing exactly, what types of additive manufacturing do we have, and then also what is the process and what makes it more beneficial above your CNC or your standard conventional manufacturing mechanisms. Right, so this is a fairly short slide section that we're going to do. I think it's around 15 slides, so we might actually finish with this study theme today as well. But to start off, let's perhaps first ask what is, yes. Yes, so I'll load these slides will click up after our session today. Yes. Right, so this is, just to note, this isn't one of the sections in the Shigley textbook as well. So this is just the slides that we're going to use for this section that we're going to do all this. Okay, but with regards to what is additive manufacturing, so I think you might be more familiar with the term 3D printing. And this is the process of producing an object, so a physical asset, from a CAD model using a layer-by-layer approach. Okay, so in other words, we deposit the material layer by layer when we add the material together to actually get our final object. Okay, so in other words, we have some physical object that we want to get from a digital model. Okay, so if we perhaps have a quick look at this video over here, just to illustrate. Right, so you'll notice over here we have some sort of a tool or end effector system over here. So I think this is then, over there we have the end effector that's moving around. So this is moving around on this hotbed over here is what we call it. And then it's depositing material onto this hotbed. So what it does is it creates a layer, so a cross-section of the part that it wants to manufacture. And it continues to add this layer by layer. And over here, if I just pause over here, you'll actually see, it might be a bit difficult to see over here, but you'll see there's these lines across your object. So that is then the layers that this end effector is busy manufacturing over here. Okay, and it's going to continue to repeat this process until it's manufactured the last layer, or the final object is then completed. Right, and we can see over here we can also manufacture quite complex geometries, and it's fairly easy to do this with a 3D printing process. With CNC you would need some sort of a specialized tooling to manufacture maybe this sort of a beehive formal pattern that you have over here. With the 3D printer it's much easier to do that. You just need a single end effector and the material that it's going to deposit. Right, so here we can also see a few other complex geometries that's being manufactured. This is just a slide mechanism that the arm or the end effector is moving on. Right, so then just going back to our slides. Right, so this last picture that I then have over here is just to illustrate the difference that we have between additive manufacturing and our more conventional subtractive manufacturing mechanisms. So CNC machining, for example, is subtractive manufacturing in the sense that we start off with some sort of material over here. So it might be a rod or a block of material. And then what we do is we actually subtract, we take away some of this material. Okay, so we might want to drill holes into this to get this sort of a 3D object at the end. So there's quite a lot of waste that goes into the subtractive manufacturing techniques. Whereas with additive manufacturing, we also start with some material, and it might be powder-based, or it might be some filament or resin that we use over there. But in this case, with additive manufacturing, we only add the material that we need to get this 3D object. There is a small amount of waste, and this is typically when you manufacture the part using 3D printing, you would want some support structure to be in place as well. So that's just to make sure that it doesn't topple over or break during the 3D printing process. So just making sure that that structure adds some stability and strength to the manufacturing of this part. Okay, so we can already see that some of the benefits over here is then we have waste reduction, and we also saw from that video that we can manufacture some complex geometries, which is not as easy to do with subtractive manufacturing or CNC methods. Okay, so to perhaps then illustrate the advantages of additive manufacturing compared to CNC, I've also set up this table. So if we work through this, we can see that it's easier to actually create the physical asset from a digital model in the sense that we only need an STL file. So what we would typically do in the process is we first create our CAD model, and then once we have that in place, then we can convert our model to an STL file, and we simply give that as an input to the 3D printer, the additive manufacturing system, and then from there it will take it further and manufacture the part. Okay, with CNC manufacturing, it's significantly more effort that you would require to manufacture parts. Reason being, you will first need to go and parameterize the digital model. So some of you might have heard of the G codes or the M codes that your CNC lathes or your multi-axis machines use, and the milling machines also use. So in that case, what you might want to do is parameterize the digital model in the sense that you first have to go and figure out the mathematics or the geometry of this part and how it's going to manufacture it. Okay, so then with 3D printing, we can also perform this using a single tool or end effector, and if we want to, also a single material. So the reason for that is we simply deposit the material using that end effector, and depending on the type of additive manufacturing that we use, that will determine the type of material that we need and the end effector that will be used throughout. With CNC manufacturing, however, the processes usually involve complex tooling choices and arrangements to achieve multiple operations. Okay, so if we, for example, want to do, let's say, end milling, and we want to do some drilling on the part as well, we're going to need different tools for those kind of operations over there. So in that case, we might need a CNC machine that has more than one tool post so that we can quickly cycle between those tools, and we also need to determine the offset, all those kind of tool parameters that are dependent on the tools that we're going to use. Okay, so then also for 3D printing, very little setup time is required. So once you have your CAD model and your STL file in place, then it's only a matter of doing some final calibrations, and then it's simply plug and play and waiting for the part to be manufactured. With CNC manufacturing, however, if I want to cycle between different parts that I want to create, there's probably going to be some significant change over times that I'm going to need, and the setup is also going to change for each part that I want to manufacture. Okay, so in other words, then I have to redo my parameterization and the calculations. I have to set up offsets if I use different tools for the different parts. And then I'll probably have to do some test runs and tooling changes as well, if the tool perhaps breaks or if some of the tolerances are out of place. Then I need these test runs to see how the part will look, and so that I can test it using measuring equipment. Okay, and then lastly, over here we also said that we can create complex geometries, and we can easily model and manufacture this using the 3D printers. With CNC manufacturing, however, the efficiency of the processes are greatly underpinned by the model complexity that we're using. So the more complex the part is that we need to manufacture, the more difficult it is, or the longer it's going to take to manufacture the part as well. Okay, so this doesn't necessarily mean that additive manufacturing doesn't have any disadvantages. CNC is still quite relevant in today's industry. So if we want to perhaps compare the disadvantages of additive manufacturing with regards to CNC, we can use this table over here. So for 3D printing, there are quite limited material types that are currently supported. So yes, we can use different metals and polymers or ceramics and manufacture with that. But compared to CNC, there's a much vaster range of materials that we can use. Anything from your high-strength steels over to polymers, and anything in between as well. Okay, so then another disadvantage is that 3D printing typically has lower accuracy and precision due to its aliasing or layering capabilities. So because it's generating this in a layer by layer, we saw from the video as well that you can see those layers actually forming on the surface. So that already tells us that we're not going to be able to attain the surface finishes or the fine micron type tolerances that we have with the new CNC machines. Okay, so with CNC manufacturing, we can typically achieve extreme tolerances of less than 20 microns if we use specialized tooling or specialized CNC machines as well. Okay, and then with regards to additive manufacturing, it's also typically a poor choice for mass production. Reason being, it is quite good for rapid prototyping, so you don't have to set up all the tools and everything, but once you start with creating these large 1,000, 10,000 batches, then it gets a bit more difficult to achieve the efficiency that we have with our CNC machines. Okay, so once the CNC machine is actually set up, if it has to run a large batch, then it's fairly easy to do that. The only thing that we'd rather want to look out over there is just making some offset changes during the operation, and then also tooling changes if any of the tools break. Okay, so just a few last benefits as well that we also mentioned previously. So firstly, we said about waste reduction. We said since additive manufacturing simply adds the amount of material that it requires, we have significantly less waste over there than what we would have for subtractive manufacturing. And then it's also more applicable to the end user in terms of the cost and size. So over here to the right, you'll see as an example of a 3D printer that one would perhaps want to buy. In this case, we can use two different filaments over here that is then deposited onto this hotbed. And this is fairly cheap compared to CNC machines. So you'd much rather want to invest in a 3D printer if you want to do prototyping than a CNC machine. Okay, and then we also said it has these rapid prototyping capabilities. So once I have a CAD model, I can simply plug it in, see how it looks once it's manufactured, and I can take it from there. Okay, so then there's just this process as well. So when we want to move then from the digital environment to the physical asset using additive manufacturing. So I think it's a bit small, so I'm just going to zoom in. All right, so the first step that we would want to start off with is actually creating our CAD model. So we create this 3D digital model using some software tools that we have available. So anything like SolidWorks or AutoCAD or FreeCAD. Once we have this model in place, then we simply want to convert it. So the CAD model is then converted to this standard triangle language or STL. So this is the standard file type that is used by most 3D printers and in the 3D industry. And these STL files over here, we also said it's, we now said it's commonly used in 3D printing technologies. So once we have the STL file, we can simply take that over to the 3D printer machine, and we do some machine configurations over here. So we load the material that we want to use. If we need any calibration, so with regards to the offset between the end effector or the depositor and the hotbed, then we can do that over here. And then we also set up any other printing parameters that we might want to use as well. Okay, and then it's simply a matter of waiting for the 3D printing to process to actually execute and be finalized. So the part is then printed using the provided parameters and the material. Once the part is then manufactured, we can move on to removal and cleanup. So then any supporting structures are then removed. So the structures that the 3D printer would use to simply increase the stability, but that is not really a part of the actual object. We can remove that. And then removal of unwanted features as well. So if there are any burrs or anything, we can remove that as well. Or any flakes of the material that's still present. And then finally, we could also do post-processing. So if we want to make any refining, any remaining refinements, then we can do some cleaning or polishing or painting of this part. And once that is done, we have our finalized object. Okay, so with that in place, now we can move on to the different types of additive manufacturing. Okay, so the type of additive manufacturing that we are most used to, or that we know of, is this material extrusion. So that's also, if you go and look at these parts or you look at these 3D printers, you'll see most of them use the material extrusion technique. So that is simply where you have some end effector that is then depositing the material. So you have some spool with wire, plastic wire, that is then unwound, and that is then deposited through the nozzle. Okay, but in fact, we have a bunch of other additive manufacturing types as well, and it depends on the application that we want to achieve. So in addition to material extrusion, we also have this sheet lamination over here. Then we have binder jetting and material jetting, directed energy deposition, or DED for short, and then powder bed fusion. And finally, we have some of these UV type additive manufacturing techniques as well, like this VAT photopolymerization here. Okay, so if I just zoom out a bit, then we're going to discuss this thing on the next slide. Okay, so starting off with material extrusion, what we do over here is we have some heat-sensitive material that is pushed through a heated extrusion nozzle, and it then deposits this material layer by layer. So if we look over here to the right, you'll see we have our hotbed or our build platform over here, and then this is the support over here. So what this nozzle does, if we have the filament spool over here, it actually unwinds this material, it goes through this roller, and then we have this heating element over here, which then liquefies the material, and the nozzle then deposits it layer by layer when it's manufacturing this part. Okay, so a fused filament fabrication is probably the most common material extrusion process that we use. So in this case, the material is then deposited layer by layer, and as the material actually cools down and it solidifies, it then fuses with the other layers that have already been placed. Okay, so if I have this initial layer here at the bottom, once I deposit the next layer, then that will actually fuse with the bottom layer. So it adds some strength and stability to your system as well. Okay, so the type of materials that we use over here typically have a high strength to weight ratio. So stuff like ABS or PLA, those kind of plastics or polymers that you want to use over there. And then the applications that we want to use this type of 3D printing for would be in the prototyping of any automotive components. It's also used in the medical and aerospace the medical and aerospace fields as well. So perhaps if you want to prototype some medical implants, you can do it using this method, and yeah, then your aerospace components as well. Okay, so then the next method is this sheet lamination that we have over here, and the definition or the name is sort of self-explanatory in the sense that you have some sheet that is then being unwound, and then this is being cut to a certain size over here, and then we simply add this layer by layer again. Okay, so over here we just have a process that we follow. So rapid prototyping process where sheets of material are then joined together to generate an object. So we have a roll of material that is introduced on the build surface. So this build surface is this surface that we have over here. And a bonding adhesive is then applied to the build material. A heated roller then moves over the surface to bind this material, and a laser beam or a knife is then used to cut the sheet according to the 3D CAD model data that we give it in. And then we simply repeat this process for any subsequent sheets as well. Okay, so over here, just to show you, over here we have the rollers with the sheet, and what we do is we just stretch it out. Then we have this heated roller that's going to move over it, and it binds it to the previous sheets that have already been cut. And once the binding is done, then the laser comes in and just cuts away the material that it doesn't need, or the part of the sheet that it doesn't need. Okay, so applications for this would include any paper-made objects, and also topography visualization. So perhaps if you want to create some sort of a 3D contour plot, then you can also use this type of sheet lamination manufacturing. Right, so then moving on to binder jetting. In this case, we have still a layer by layer printing process, but now we have that the building material is applied to the print bed, and then it's selectively bound by the print head according to the 3D CAD data. So we have some sort of a binding agent over here that is then being deposited by this inkjet print head over here. All right, so the build platform is adjusted by 1 layer thickness, and the process is then repeated until the object is finished. Okay, so once we've added, let's say here at the bottom, our first layer of powder, then the binding agent comes in, binds the part that it requires, and then once that is done, it moves on to the next layer and binds that layer as well. Okay, so in this case, we can actually support a vast range of materials. So we can do anything from ceramics to polymers and also any composite materials if we want to. The applications for this type of manufacturing or AM technique include metal part prototyping and production, where we need minimal post-processing. So you'll notice that since we're working with a powder bed over here, the amount of support structures is significantly less than what you would have for let's say material extrusion. Yes. So 3D printing, I think it's still additive manufacturing. So we use the two terms interchangeably. So this is still 3D printing, but I think what you might be referring to rather is material extrusion. So with material extrusion, yes, we have we have the material that is actually liquefied, and that then creates the part once it's being layered. For binder jetting, on the other hand, we have some powder material in place. So this powder is then just merged to one another or glued together using this binding agent. So you'll see over here as well, they refer to a liquid binder. So that is then deposited through this nozzle over here. Yeah. Okay, so then with regards to material jetting, so you'll notice over here, so previously we had binder jetting. So in that case, the binding agent was being deposited by the nozzle. In this case, we have material jetting. So in that case, the material is then being deposited by this nozzle. Okay, so this is a full color AM technique whereby thermoplastic droplets are then discretely deposited. So this is similar to the way in which an inkjet printer dispenses individual droplets of ink when it's printing something. Okay, so if I perhaps zoom in on this figure that we have here to the right, you'll see we have some photopolymer material, and then we have a support material over here as well, and then we have the nozzles over here. So this then deposits the material that we have over there, and then we have some sort of a UV light over here, and this is simply used to solidify or to cure the material that we're depositing over here. Okay, so over here we also say that a UV source is used to harden or polymerize the layer of deposited material, and the process is then once again repeated for each layer. So it's still a layer by layer additive manufacturing technique. Okay, so for the applications for this one, it includes casting patterns, cores, and molds. So if you want to create some sort of a mold to use for other parts that I'm going to manufacture, then I can use this material jetting technique. And then of course we also have these aerospace applications and medical and surgical models as well. So this would be some anatomical models that you would want to create using the material jetting process. Okay, so then moving on to 5.5, which is then the directed energy deposition or DED method. In this case, the metal powder or the wire is melted using a heat source such as a laser or an electron beam. So the melted metal pool is then applied using G-code to the specified surface where it hardens to a solid structure. Okay, so if you look at this figure over here, you have some sort of an existing part or perhaps a bed in place over here. And then what this system does is it has some powder material together with the powder feeding gas and the shielding gas, which then gets deposited. And as this gets deposited, we also direct a laser beam at the material. So it then melts that material and adds it to this substrate of this system that we have here. Okay, so this method is quite common for modifying or repairing existing components. Okay, so since we directly melt this material, we can just apply it over here to an existing component. We have a deposited layer, and then we have this melt pool over here, which is just as this thing is moving along, it will create this melt pool. So this is perhaps similar to what you would see in welding, arc welding, where you have some melt pool over there, which then translates together with the welding rod. Okay, so then 5.6 is powder bed fusion. So you'll notice it looks similar to what we had for binder jetting, but in this case we actually use a laser beam instead of some binding agent. So we simply direct the laser beam into this powder bed that we have over here. So we start off with a thin layer of powdered material that is then spread over this build stage, and then we simply use a heat source to apply and scan over and then fuse the powder into a first cross section of the part. Okay, so in other words, if I start off with a very thin layer of material over here, then this heat source or this laser beam will come in and it will simply direct the laser beam along the actual cross section that I want to create. Okay, and once again, the process is repeated on a layer by layer basis until the part is then complete. And the nice thing is that we don't need any support structures in this case, so we significantly reduce the amount of waste that we need using this additive manufacturing technique. Okay, and then there's just a few different types of powder bed fusion as well, depending on what type of heat source we use. So that would be laser fusion. We also have electron beam fusion, this agent and energy fusion, and then finally thermal fusion. So thermal fusion where we just use some heat source. Okay, so this is quite suitable for both plastic and metal parts, and then the applications also include medical implants, any research and development applications where you would like to do some rapid prototyping as well. All right, so then the last point that we want to look at over here is just with regards to VAT photopolymerization. And like we said, this is a light source based method, and in this case we also don't use some powder or some wire over here for our material. We actually make use of a resin, okay, so a liquid over here. So a VAT containing photosensitive liquid resin is selectively cured layer by layer using a suitable light source. So in this case you'll see, if I zoom in, you'll see there's different types of light sources that I can use, so either laser, UV light, digital screening, or LCD screen, any of those kind of things as well. So after the object has been created, we simply submerge it in a chemical bath to wash away any excess resin, and it is then further strengthened and hardened by placing it inside an ultraviolet oven. Okay, so different 3D printing technologies are then encompassed by this VAT photopolymerization method. So we have over here stereolithography, digital light processing, and then also this clip or continuous liquid interface printing methods. Okay, and once again we see some of the applications over here, or the predominant applications for these type of additive manufacturing technologies is within the surgical environment, also prosthetics, and then hearing aid manufacturing as well. Okay, so with that being said, then just the last point with regards to what we've then covered. So we said that additive manufacturing has quite good advantages over CNC applications, especially for the end user, mainly for cost effectiveness, manufacturing speed, especially if you're considering rapid prototyping. And then also if you have some complex designs or complex geometries, it's much easier to perform these manufacturing techniques using 3D printing rather than CNC technology. Okay, then the process from digital to physical assets is also somewhat simplified in additive manufacturing, so making it more user-friendly than your conventional CNC manufacturing methods. Various types of AM or additive manufacturing technologies exist, and it also depends on the application, the material that you would require, and then also the available assets, as well as the cost implications. So how much are you willing to spend to manufacture this part or to do some prototyping. Okay, so additive manufacturing is also a technology that continues to grow with the expansion of our digitalization and end user applications. So perhaps if I just show you on this website over here, just say allow, you'll see if you go all the way down, there's actually a few new additive manufacturing technologies as well that they discuss over here. So it's definitely a manufacturing technique that is continuing to grow, and it will probably grow together with the digital era that we're living in. Right, so any questions with regards to additive manufacturing? Okay. Right, ladies and gentlemen, that was then the AM study theme. So yeah, we'll wrap up here for today. Okay, thank you.